Of the paper I'm presenting today is comprehensive deadlock prevention for GPU collective communication. My presentation is divided into 4 parts. Let's begin with the introduction. Okay, the DN parameter scale and training data size continue to expand. In this context, distributed DN training techniques are developing swiftly and widely applied. Okay, based on the partitioning methods of training data and DN model parameters, common distributed DN training approaches are categorized into data parallel, tensor parallel, and pipeline parallel. And GPU collective communication is used to synchronize DN status and play a critical role in distributed DN training. The figures here illustrate the commonly used GPU collective communication operators in distributed DN training. Okay, and Nico is currently the most popular GPU collective communication library. The figure here shows the throughput ratio between Nico and CUDA-aware MPI, indicating that Nico achieves a throughput up to 6.7 times higher than that of MPI. Nico improves throughput because it abandons the CPU-side control plane and adopts GPU-side control logic based on bit weighting and polling, efficiently utilize the inter-GPU communication bandwidth. However, such a design also makes Nico-based collectives inherently prone to deadlocks. Then GPU collective deadlocks pose a significant threat to distributed DN training. The issue of GPU collective deadlocks is widely recognized, but there is currently a lack of a comprehensive solution. Many foundational software libraries used in distributed DN training only warn of the potential deadlock risks, but are unable to effectively prevent them. The reason GPU collectives are prone to deadlocks lies in the fact that it inherently satisfies 3 out of the 4 individually necessary and jointly sufficient conditions for deadlock, namely mutual exclusion, hold and wait, and no preemption. Okay, therefore, once an application causes a circular weighting of collectives, deadlock occurs. Okay, in the application, disordered invocation of collective operators on different GPUs may lead to circular weighting, resulting in deadlocks. Besides, GPU synchronization makes circular weighting and deadlocks more likely to occur. The GPU synchronization operation will block the device until all launched kernels on the GPU have completed execution, thereby introducing a dependency of idle resources on allocated resources. These figures here illustrate the legal and the deadlock situations. In the figures, both collective A and collective B execute on GPU 0 and GPU 1. The diamonds within each GPU represent the resource units required to execute a collective on that GPU. Solid arrows indicate that a resource unit has been allocated to a collective. Dashed arrows represent the collective applying for a resource unit from a GPU. Outlined red arrows depict the dependencies of idle resources on allocated resources introduced by the GPU synchronization. When an application invokes collectives in a consistent order on each GPU, like here, invoking collective B before A on both GPU 0 and 1, these collectives can execute normally. When application invokes GPU collectives in different orders on each participating GPU, like here, GPU 0 first invokes collective B, followed by collective A, while GPU 1 invokes them in the opposite order. If these collectives are issued to different streams. What? Okay. Oh, sorry. Streams and resources are sufficient, these collectives can execute normally. And when collectives are launched in the same stream or when resources are insufficient, the disordered invocation of collectives across different GPUs results in circular collective dependency and a deadlock. When two GPU invoke 2 collectives in opposite orders and both issue GPU synchronization after invoking one, the disordered collective invocation and the resource dependency introduced by GPU synchronization together leads to the circular collective dependency and deadlock, even though resources are sufficient. The figure on the right illustrates the status of collective kernels when deadlock occurs. On GPU 0, the kernel B0 of collective B launches, occupies the resources allocated to it, and begins polling and busy waiting for the corresponding kernel B1 on GPU 1 to launch. However, at this point, B1 cannot acquire the necessary resources to be scheduled for execution because A1 on GPU 1 is still busy waiting. As a result, both B0 and A1 become trapped in the endless busy waiting, causing a deadlock that requires manual termination of the process. Existing methods prevent circular collective dependency by ensuring that collectives are invoked in a consistent order across GPUs without managing GPU synchronization. There are three main limitations of existing methods. First, they are hard to develop and verify. Second, they are tightly coupled with specific scenarios. Third, they cannot completely eliminate the risk of deadlocks. Okay, next, I will provide a detailed introduction to DFCCL, the deadlock-free collective communication library. First, I will introduce the primitives that compose GPU collectives, and then highlight the opportunities for preempting GPU collectives. The topmost figure illustrates the 4 buffers used in GPU collectives. Send-receive buffers are local buffers for input and output. Send-receive connectors contain lock-free ring buffers used for inter-GPU data transfer. The send action writes data to the send connector, while receive reads data from the receive connector. And the reduce action reduces data from the send buffer and the receive connector with a specified reducing function. And the copy action puts data into the receive buffer. Every primitive is a fusion of basic actions. The figure on the right illustrates the primitives used in the reduce scatter operator. And each primitive includes one or both of the send or receive actions. Based on the presence of send and receive actions, the primitive busy waits until the send connector is writable or the receive connector is readable before progressing. By limiting primitive's busy waiting time, we can abort its execution, thereby preempting the associated collective. Moreover, the persistent visibility of written data enables individual GPUs to independently preempt collectives in a decentralized dynamic manner without explicit coordination among GPUs. The persistent visibility of written data means once a GPU writes data to the send connector for a collective's primitive, the data remain visible to the peer GPU. The visibility persists even if the collective part on this GPU is preempted after writing, or the corresponding collective part on the peer GPU is preempted before writing. Okay, the upper figure here illustrates the overall architecture of DFCCL. DFCCL consists of GPU and CPU parts. On each GPU, the daemon kernel is the core component and manages execution, scheduling, and preemption of an arbitrary number of dynamically submitted collectives. The FCCL CPU component manages asynchronous non-blocking request submitting and completion notifying based on the submission queue or SQ and completion queue or CQ. The collective invoker inserts a submission queue element or SQE into the SQ and records a collective ID callback pair in the callback map. The daemon kernel periodically checks the SQ, fetches and parses SQEs, and executes the requested collectives. The daemon kernel inserts a completion queue entry or CQE for each completed collective into the CQ. The polar thread monitors the CQ. Okay, once the polar finds a CQE, it executes the callback tied to the collective, which notifies the invoker of the collective's completion in the user-defined way. The code block below demonstrates the APIs of DFCCL. Okay, the figure here demonstrates that the key components of the daemon kernel. The daemon kernel parses the SQEs and maintains the invoked collectives within the task queue. The daemon kernel executes the primitive sequence of the scheduled collective in a two-phase blocking manner. The daemon kernel assigns spin thresholds to the collective's primitives to limit the busy waiting time. During execution, A primitive first pulls up to spin threshold times to check if the condition required by the send or receive action is met. If the primitive cannot execute after polling spin threshold times, it is aborted, and the associated collective is preempted. DFCCL's daemon kernel schedules collectives via the adaptive stickiness adjustment scheme. The stickiness of a collective indicates the daemon kernel's willingness to wait for its progress. The stickiness adjustment policy is divided into an order adjusting policy and a spin threshold adjusting policy. For the order adjusting policy, either FIFO ordering or priority-based ordering can be utilized. The FCCL's automated adaptive spin threshold adjusting policy assigns the largest initial spin threshold to the collective at the front of the task queue. During execution, if the daemon kernel detects that a primitive executes successfully, it raises the spin threshold of the succeeding primitives of that collective, which increases the probability that all GPUs simultaneously execute or wait for the same collective, and achieves decentralized dynamic GAN scheduling. Okay, the daemon kernel voluntarily quits when it cannot fetch new SQEs for a certain period, and the task queue is either empty or contains only collective that cannot progress. The daemon kernel voluntarily quits for two reasons. One, to release the GPU resources for other tasks when it's idle, and to prevent deadlocks related to GPU synchronization. Once the daemon kernel quits, the blocking GPU synchronization can complete, thus allowing stuck collectives to proceed. And DFCCL tries to start the daemon kernel upon SQE insertion to the SQ, or when the inserted CQEs are fewer than SQEs. The daemon kernel is initially launched up to the insertion of the first SQE. DFCCL has three main advantages. First, DFCCL's library level APIs can be invoked concurrently and synchronously without the risk of deadlocks. This ensures that circular waiting no longer results in deadlocks. This figure illustrates that DFCCL can proactively abort collectives that stuck in the busy waiting and schedule other collective for execution. This mechanism prevents GPU collective deadlocks and ensures the correctness of distributed DN training. And secondly, DFCCL provides high performance assurance. And thirdly, DFCCL maintains independence from various distributed DN techniques. Next, I will present the results of the experimental measurements. Specifically, I will discuss the results across three categories of benchmarks: DFCCL's deadlock preventing capability, the bandwidth and latency of collectives, and the performance of DN training. Experimental results show that DFCCL can effectively prevent GPU collective deadlocks, ensuring that processes consistently make progress without entering endless polling. While possessing this capability, DFCCL introduces minimal overheads and achieving performance comparable to Nico across various benchmarks and even surpassing Nico under specific conditions. The figures here illustrate the examples of execution of two test programs designed to verify DFCCL's deadlock preventing capability. The first example involves disordered invocation of collectives, while the second one inserts GPU synchronization operations into the disordered collectives. In these two test programs, DFCCL effectively prevents deadlocks over 200 iterations of experiments through preemption and voluntary quitting of daemon kernels. In contrast, when using Nico, GPUs encounter a deadlock after initiating the first call. Okay, these figures here illustrate the performance of 5 types of collective operators in terms of bandwidth and latency under various development scales and buffer sizes. The experimental results demonstrate that DFCCL achieves performance comparable to Nico and outperforms Nico in certain cases. These figures illustrate dynamic average training throughput of vision transformer under different distributed training techniques. Experimental results indicate that the difference between DFCCL and Nico falls within plus or minus 3%. And here the figures here illustrate the per iteration training time of GPT-2 using 3D hybrid parallelism based on PyTorch and Megatron LLM. Experimental results indicate that the difference between DFCCL and nickel falls within plus or minus 4%. And the figures here illustrate the average training throughput of data parallel ResNet 50 training. Experimental results show that DFCCL has comparable throughput to statically scheduling of OneFlow. Additionally, DFCCL achieves a performance improvement of 20.4% to 22.3% compared to Kung Fu and Harvard. Okay, finally, I would like to conclude by summarizing this work. GPU collective deadlocks pose significant threats to distributed deep learning. This paper introduces DFCCL, which effectively prevents the GPU collective deadlocks and maintains high performance. The code of DFCCL is open source and available here. Thank you.